Hello, so this is a revision video for IB Chemistry S1.3.1, Emission Spectra. This is a revision video, so we only cover the essential information that you need to know. For more detailed explanations and for full video lessons, please check the links in the description below and visit chemistrystudent.com. When an atom absorbs energy, electrons in the atom can jump to higher energy levels. They reach what is called an excited state. However, an electron that has reached an excited state will eventually fall back down to a lower energy level. And when it does, it will release energy in the form of light, photons. As electrons can only exist at certain energy levels in an atom, they can only release certain amounts of energy as they fall back down to a lower energy state. This means they will only release specific wavelengths of light, because remember, a different wavelength of light corresponds to a different amount of energy, and as well, a different wavelength of light is a different color. This means if we study the light emitted by an atom as its electrons fall back down to lower energy states, we would see only specific amounts of light being released by that atom. And this is what we observe with an emission spectrum. A commonly studied emission spectrum at this level is the hydrogen emission spectrum. The hydrogen emission spectrum shows the specific energies emitted by electrons as they fall to the n=2 energy level from higher energy levels in an atom of hydrogen. A continuous spectrum contains all visible wavelengths of light without any gaps in it. It looks like a rainbow. All the different possible wavelengths of light are present. A line spectrum, however, shows only specific wavelengths of light. Each line corresponds to a specific wavelength, and in the case of emission spectra, each line corresponds to an electron falling from one particular energy level to another. Line spectra are like fingerprints. They are unique to each element. The electromagnetic spectrum includes many different types of radiation, from radio waves to gamma rays, and they all differ in their wavelength, frequency, and energy. However, they are all electromagnetic waves, which means they're all technically light waves. Even if we can't see them, the section of the electromagnetic spectrum that we can see as humans is the visible region, approximately 400 to 700 nanometer wavelength. Red light has the longest wavelength at about 700 nanometers and the lowest amount of energy, whereas violet light has the shortest wavelength at about 400 nanometers but has the highest energy. Energy, frequency, and wavelength are linked, with higher frequency meaning shorter wavelength and higher energy waves.